Bismillahirrahmanirrahim. Assalamu alaikum students, and let's start with our new lecture. In this, we'll basically stepping into the domains of complex engineering problem. But before that, I think it is very important to give you guidance and practically show you an application which is very useful, especially from the mechanics of material point of view. And if you understand this software well, it can solve you a lot of problems for solid mechanics 1, solid mechanics 2, and it has also a lot of applications uh, in your final year stress analysis, and then you will be also dealing with your final year projects design, which you will be selecting design projects for final year. It can help you, especially from the solid mechanics and design point of view, and it's also helpful, especially if you take projects similar to for petroleum oriented design final year projects. Okay, so like just to let you know that we have our one of our questions was like this question, if you remember, uh, we have done it in our shear after doing bending, asymmetric bending, and all these things. After doing shear, we solve this numericals like it says a metal beam with span L equal to 3 feet is simply supported at points A and B. Okay, these are the A points is the pin and the roller. The uniform load on the beam, including the weight, is this pounds per inch, 160 pounds per inch. The cross section of the beam is rectangular. They are saying it is rectangular uh, with a height of 4 inches and the width of 1 inches. Supported against sideway buckling. They say the beam is adequately supporting against sideway buckling. So it because of the load which is being acting, it will not buckle. They have reinforced it. Now you need to determine the normal stresses at a point which is C, and the shear stresses at C, at point C, which is located 1 inches below the top of the beam and 8 inches from the right hand support of the beam. Show these stresses on the sketch of a stress element at point C. Okay, if you just look at it, this point is somewhere is here. This is the point C. Okay, so from here, if you look at it, 8 inches from the right support. This is the left support, this is the right. So 8 over here, if you look at it, 28 from here, inches. And from the right support, and it says that it is located 1 inches below the top surface. So 8 inches and 1 inches, if you look at it, this is the coordinate of this point C. And if you start from the left hand support, it will be like 28 inches and 1 inches. Okay, and these are the cross-sectional details, 4 inches by 1 inches. This is B and this is the height H. So centroid will be at about 2 inches from the top and 2 inches. If you move from the bottom, you go up, it is 2 inches. So we're going to take this as our respective area for in order determination of the cube. And as you know, it is from the top surface. It can also be from the bottom surface. Remember I told you, but we're taking it from the top surface, and from the centroid it will be at 1 inches. Okay, 1 inch and 1 inch. And we'll be interested in the centroid of this 1 inch. Okay, so just you already know this, I know, I have told you before, but just a reminder over here. So this problem is here. If you look at it, this is the loading. 160 pounds per inch is the loading, and total height. This total height is 4 inches. Okay, and total length is 3 feet, which is 36 inches. So if you look at it, we go to the solution of this problem. Uh, this was our week 6. So So the same beam, here it is, and this is 8 inches, more clear, conspicuous. This is the cross section details. So here we did what we need to find sigma c, tau c. So we take the reactions, uh, obviously apply sigma fy, and we get 5760 for equation 1. We apply moments and b, and we get these are the reactions. 2 it is 0 pounds, and RB is 2880 pounds. Okay, so we are interested in basically we want to find the bending stress and the shear stress at a very unique point, not at a midpoint, but 28 inches, because 8 inches from there, so it will be 28. 28 plus 8 is 36. So when we calculated that, we get the bending moment at C, the point of our interest is exactly C. So it is not going to be X, but because this is the exact point of interest, so we made it 28, it's not X. They just don't get confused at this point. So we get the bending moment at C is equals to 17920 pounds inches. And when we apply sigma Fy, we get the shear force, this Vc is equals to minus 1600 pounds. Then we go and we calculated the moment of inertia for the cross section. This is the cross section, okay, 1 by 12 bh cube. It's a rectangular cross section, so it comes out to be equals to 5.33 inch 4. Then the bending stress is my upon I. Okay, since it is above the neutral axis, so we take the minus sign. And what was the bending moment at C 17920? Y is half the distance from the neutral axis. I just calculated at the top. It comes out to be minus 3360 psi. And then we basically calculated the shear stress. And for the shear stress, we know that our specific area of interest is 1 inch square. So the centroid of that will be what? It will be 1 plus the centroid of this dark shaded area, 0.5. So it will be 1.5. Just a brief reminder, it comes out to be equal to 1.5 inch. So now we are interested in the first moment of area is QC is equals to AC into YC is 1.5 inch cube. So tau C is equals to VC QC over IB, and it comes out to be equals to shear force at C. VC was 1600 into QC 1.5, 5.33 was I, moment of inertia, and the width was 1 inch. So the shear stress comes out to be equals to 450 psi. It was our shear stress. Now basically the normal stress was minus 3360 psi, which means it was compressive at that specific point of C, and the shear stress comes out to be equals to 450 psi. Regardless, it can be minus or plus, doesn't matter, because shear stress can either be clockwise or anti-clockwise. You can also make it as 450 psi because it doesn't matter. It can be clockwise, it can be counterclockwise. So both answers are correct. Don't get confused into that. Okay. So here we open this software, and it is called as the MDS, the mechanical design MDSolid. It's called MDS or MDSolids, okay, precisely speaking. So it has got different array of modules, sub modules built into it. Like if you want to perform the trusses analysis, you can calculate the forces and deformations. You can get over here unknown forces, not deformation, unknown forces, general analysis for torsion beams, pure torsion, determinate beams, okay, the bending problems, the flexure, the section properties, and the Mohr circle, okay, and the combined loading, which means I've told you before, in which you have more than one loading acting into your system, is called an example of combined loading. The pressure vessel systems, okay, very much important in stress analysis, and over here you have already studied machine design, EMD1, EMD2, and also pressure vessels designing is very important in solid mechanics also, and then columns, okay. So let's start with because our problem, if you look at the problem here, it is the beam on which the loading is there is as 160 pounds per inch is the loading, okay, and these are the cross sectional, and this is a simply supported beam. One side is pinned and the other side is roller, okay. So we go and we know the properties of our section was 4 inches by 1 inches, okay, and they have put the section as vertically like this. They can also put it like horizontally, but they haven't done that, and I know the reason why. You know the reason why they haven't done it, okay. So let's go to the section. When we go to the section properties, we have got simple, flange, double, standard, help. Uh, we will be following the simple rectangle shape here, and we have two options. Here they have placed it as YZ, and our dimensions are in inches. So we write it as inches, and this height is 4 and this is 1 inch, and this is 0, and we call the, because they say it's a steel metal beam, it is a steel metal beam, so we have got some, we have to calculate its modulus of elasticity. So we take the standard as, say, one of the most easily available material and quite robust and applied in Pakistan is this steel A36 structural. We take this, and this is its properties, 29.1 E6, 29 E6 psi, okay, and we want to know this section moment of inertia. If you want to know the section moment of inertia, we ask the software to calculate, and it has given us the results. If you look at it, moment of inertia is 5.33 inch 4, section modulus is 2.667 inch to the power 3, okay, and if you look at it here, uh, our moment of inertia was 5.33 inch 4, see, and then we go, okay, why they from a technical point of view, why they haven't put the cross section like this, just an answer why they haven't put it like this, okay. You see, and I compute now, you see what happens here technically. See, the moment of inertia dips down to such a low value. See, the section modulus has dipped down to some drastic value, and lower the section value, higher will be the stresses generated in the beam, so resulting into the failure. So we don't want that model design. So we just shift it up again, and we make it like this, and see, now it's okay, 5.33, and this is the section modulus. We can get the product moment of area, the moment of inertia, all has been received, okay. So we go back, and we go to here, we say determinate structure, and you know the data. So total beam length is 3 feet. So if it is 3 feet, so let's say it is 36 inches. Now left support is 0. What is the right support? 36. Here it is. The loading is a UDL acting downwards, not upwards, downwards. And it starts at 0 and it ends at 36. And what is the load magnitude? What is the load? 160. Be very careful, do not use this because it will be different units, so answer will come erroneous, different answer. It is pounds per inch, and we do this. See what we get here. If you look at it very carefully, this is our model. W1 is 160, it is paint over here, roller support over here, and if you look at it, what was our reactions? Are we doing right? RA2 at 0 pounds, RB2 at 0 pounds. If those were our reactions, let's go and see the beam diagram. 2 at 0, 2 at 0. Okay, what was the maximum bending moment at the midpoint? You know, wherever shear force becomes the 0, what is happening to the bending moment? We're getting the max bend. Other thing is that this is the load diagram, this is the shear diagram, okay, and this is basically the moment diagram. So we can also get here, this was shear force and bending moment diagram. We can get another property. Here it is. We get slopes and deflections as well over here. If you look at it, for this diagram, this is the load diagram, this is the slope diagram. This is the slope diagram, which is in degrees. You have the liberty to make it because you know precisely it has to be in radians. So let's say now it is in radians, and these are the deflections as a result of this UDL. So if you go down, if you see, we want it in inches, because you are in English units. This is the deflection for that respective UDL. You have the option of a cantilever here, here. But you have to be very careful. This is all determinate cases, statically determinate beams. Okay. So now we have done the shear. This is the shear movement diagram, shear and bending moment, shear force bending moment, slopes, deflections. We got it right. Now let's go to what he says. We are very much interested in also because I have told you in theory we have done the stresses and the deflection part. So let's go here and see what happens now. Now beam stresses and deflection, but what we want here is basically this is our slope deflection diagram, and but this is our shear moment diagram. Okay, so we are interested in a way not the point 0, but we are interested in a unique point which is 8 inches from the right support. So uska matlab it means that we are 28 830 से 28 inches from the left support and 1 inches below the top surface. So if you look at it now, this is so shear moment diagram. We are interested in which point in inches. 28 and 8 is 36 from the left hand support. Okay, and if we calculate this, see what we get. He is telling us that at 28 inches The shear force generated at that unique point is minus 1600 pounds, and the bending moment, if we calculate at that unique point, is 17,920 pounds inches. So you see, at that unique point, when we cut the section, we are getting, as in the book, as 17,920 pounds inch, and from the book it is minus 1600 pounds. This was our I. Okay, that is, we got it till now. Let's go ahead. Uh, uh, mm. Then he is also interested. He says that this is the shear force and this is the bending moment diagram. But we are also, for the section, we know this is our unique point, this. So we have got the length as 28 inches, but the other point is 1 inches. So if I say that I need to calculate it in, change it to PSI. Okay, let's change it to PSI, and we want basically our normal stress. This is the max bending stress, 6,720 pounds inches. Okay, it comes out. But see, the normal stress is 0. Why? Just a reminder, because this is the point of neutral axis, and at the neutral axis the bending stress is going to be 0, but we have to move a bit up. So this is 2 inches and this is 2 inches. If we move up 1 inch, uh, let's go and see the coordinates. We move above the 1 inch. Now let's see what happens. The bending stress comes out to be minus 3360 psi, if you look at it very clearly. Okay, now what does the book tells us? Numerical that we have solved in our course studies, the bending stress is minus 3360 psi. Now let's go ahead and but we are also interested in the radius of curvature. You have to change it also, this one. uh, this is the normal stress and this is the inches. This is the radius of curvature. This is the 17,920 inch pound inch. This is the radius of curvature. uh, so basically it comes out to be equals to 8,633.9 inches. Okay, we also want that what is going to be the unique shear stress at that unique point. So let's see what happens. The shear stress again at the neutral axis comes out to be maximum. It's parabolic profile, and if we go and we see that at this point it's coming out to be minus 450 psi. But we see in the book, we have, here I got that. Here again, the shear stress comes out to be equals to 450 psi. The area at unique point C was 1 inch square, YC was 1.5 inch, the QC, the first moment of area, is 1.5 inch cube. So here he has calculated it. Y equals to 1 inch, Z equals to 0.00, and Q, the first moment of area, is 1.5 inch cube. Okay, and this is, as far as the numerical is concerned, that is, our job is done and we are very happy. But you being engineers, in the real world scenario, you want to know कि भाई जो मेरा ये बीम है, will he or she be able to survive the load जो उस पर वजन पड़ेगा, क्या वो survive कर सकेगा, क्या ये लोड 160 पाउंड्स इंच की जो लोडिंग लग रही है, will it break it or will it not break it? That is the point of our interest. Okay, is it, how do we tell you? One thing is that we performed finite element analysis for it. That is the best thing it will tell you. We'll compare it with the allowable stresses, and then we can compare. Another thing is that because it is structural steel, I mean, this is just not included, but just for extra knowledge being engineers, and very important from your FIP for final year. if I go here and if I write this was the units PSI and my material was A36 structural steel. Here it is. Yeah, it is steel A36 structural steel is the material. So it's giving me a PSI of 24,000 PSI under tension and compression, and shear is being taken. Say limit for both, we are taking it both. Okay. So if we do this here, ओके, तो अब हम अगर चाहें तो एंड वी गो टू द मैक्स लोड and out of this which is the most similar to our beam, this one. If I look at it, uh, this is this and this was 36 and this was length units inches and pounds inches, distributed loads pounds per inch. Okay, so everything is very similar. Now perform the computation. Okay. So see what is done. Very important. He says that based on the allowable normal stresses of 24,000 psi. ये किसकी थी? ये बेसिकली जो हमने लोड लिया था मटेरियल A36 स्ट्रक्चरल का. ये आपको किसी भी हैंडबुक ऑफ मटेरियल डिजाइन से या आपके आरसी हिबलर के पीछे एक होता है जिसमें सारे मटेरियल्स के ई मॉडुलस, इलास्टिसिटी, शियर मॉडुलस, पॉइजन रेशो दिया होता है. ये वहां से मिल सकता है आपको. द मैक्सिमल allowable positive bending moment in the beam cross section. He says the maximum bending moment in the whole cross section available is 64,000 pounds inch. ठीक है ना? यानी कि कितना मैक्सिमम पॉजिटिव बेंडिंग मोमेंट अलाउबल अवेलेबल है? मैक्सिमम 64,000 पाउंड्स इंच का अवेलेबल है. मगर जो हमारा लोड है, अगर आप यहां पे देखें, दिस वाज 160 पाउंड्स पर इंच and it was resulting in a bending movement of 25,920 pounds inch. ये यूनिट है हमारा. But the design that we have selected has the capability to for 64,000 pounds inch capability है उसकी. Okay, so it means that we are in safe waters. We are not going to be there's anything wrong with that. फिर हम वी गो टू द बीम स्पैन लेंथ एंड 36 इंचेस. फिर ये मजीद ये कह रहा है कि भाई ये तो हमने 160 लिया है, ये कहाँ तक W की वैल्यू लें कि आपका डिजाइन सेफ रहे. तो ये वो भी कैलकुलेट कर देता है. कहता है द मैक्सिमम बेंडिंग मूवमेंट इज गिवन बाय, बिकॉज सिंपली सपोर्टेड है तो इट्स ओमेगा L स्क्वायर बाई 8. देन ही सेज द मैक्सिमम मूवमेंट विल बी अकरिंग एट 18 इंचेस. द मैक्सिमम मूवमेंट विल बी अकरिंग एट 18 इंचेस एट 18 इंचेस अकॉर्डिंग टू दिस. ये तो इसका कह रहा है. सो इसकी बेसिस के ऊपर ये 18 इंच के ऊपर मैक्सिमम ये हमारा ये एड कर रहा है. ठीक है, तो ये कह रहा है द मैक्सिमम यूडीएल जिसके ऊपर आप कितना कर सकते हैं, दैट कैन बी प्लेस्ड ऑन द बीम इज 395.0 पाउंड्स इंच. यानी कि अकॉर्डिंग टू द गिवन सिनेरियो, अगर हम A36 में स्टील बीम की बात की है तो हमें बेसिकली 395 यानी कि ये जो है, अगर हमारे पास इतनी नॉलेज आ गई है कि हम इस बीम के ऊपर इसको न्यूमेरिकल को समझते हुए, मतलब बिकॉज वी आर ऑन द अप्लाइड साइड, वी कैन टेक इट 200 पाउंड्स पर इंच. वी नो वी आर सेफ. वी कैन ऑल्सो प्रिडिक्ट कि यही डिजाइन, यही मॉडल, यही प्रॉपर्टीज के साथ हम इस पे 230, 240, 260, 300 पाउंड्स पर इंच का भी लोडिंग लगा सकते हैं. और हमें अभी ये भी पता चल चुका है कि ये आपका मैक्सिमम तकरीबन 395 पाउंड्स पर इंच तक का ये जो आपका मॉडल है, ये इसका लोडिंग को सपोर्ट कर सकता है. एंड इट विल बेसिकली नॉट गोइंग टू गो फेलियर. ऑब्वियसली वी नॉट गोइंग टू गो एट 395, बट वी कैन स्टिल स्टे बिलो द लिमिट्स एंड अपना क्या कहते हैं, इसके ऊपर ज़्यादा लोड और ज़्यादा स्ट्रेस डाल सकते हैं. तो ये एक डिटेल्ड न्यूमेरिकल था. मैंने इसको स्पेशली अभी आप लोगों के लिए बनाया ताकि आपको सारे एस्पेक्ट्स जो हमने बेसिकली बेंडिंग, शेयर, फिर हमने SIB का किया था, स्टैटिकली इंडिपेंडेंट बीम्स का कॉन्सेप्ट किया था. तो ये बेसिकली आपके पास, और किस तरह से हम उसको अप्लाई करते हैं, और आपके पास एसिमेट्रिक उसका हमने बेंडिंग किया था, फिर हमने शेयर किया था, फिर हमने शेयर फोर्सेस की थी, तो ये सब इसके कॉन्सेप्ट छोटे छोटे इसके अंदर हम सब अप्लाई कर सकते हैं। तो ये एक अच्छा एक मॉड्यूल है। तो बेसिकली इसमें ये आप हम कर सकते हैं। फिर इसी के अंदर अगर हम इसको ये वापस ले आएँ और रिफ़्रेश कर दें, तो ये अगर आप गौर से देखें तो ये हमारे पास अगर ये आता है, ये आ गया। तो यहाँ पे आपको एक और मैडम ने आपको सुमैया ने कराया था चीज़ें। तो यू कैन ऑल्सो गो टू कैलकुलेट योर मोहर सर्कल ऑल्सो, इट हैज़ द केपेबिलिटी टू कैलकुलेट योर मोहर सर्कल फॉर यू ऑल्सो। अभी तो उसने हमें नहीं किया, लेकिन आपके यहाँ पे बेंडिंग स्ट्रेस और शेयर स्ट्रेस की अगर हम ये वैल्यू दे दें, तो ये आपको मोहर सर्कल को भी कैलकुलेट करके दे सकता है। अगर हम इसको ये देखें, जैसे हमने कहाँ गए, से फॉर एग्जाम्पल ये तो अपनी आसानी के लिए कर दिया, ये कर दिया। आप ज़रा देखें, इसने आपको मोहर सर्कल कैलकुलेट करके दे दिया। It has also got this unique capability for the calculation of this। तो ये आपको कई जो हमने चैप्टर्स पढ़े, तो प्रैक्टिकली इसका आपको इसका आइडिया हो गया। हमने कुछ और, आई होप ये आपको काफ़ी इंटरेस्टिंग लगा होगा, काफ़ी आपको यूनिक लगा होगा ये करके, कि आप जो भी मतलब कोशिश ये करें कि काम जो थियोरेटिकली कर रहे हैं, तो अंग्रेजी में कहावत है सीइंग इज़ बिलीविंग, तो उसको प्रैक्टिकली जब बंदा करता है तो आपको ज़्यादा मतलब इंसान को काम करके मज़ा आता है, कि आपने जब प्रैक्टिकली अपनी नॉलेज को अप्लाई कर रहे हैं। सो अब एक और मैं कुछ वीडियोज़ इसकी डालूंगा ताकि आपको मज़ीद क्लियर हो जाए। तो अब मैं कोशिश करूँगा इस हमारी थेरेटिकल नॉलेज, एकेडमिक नॉलेज को इस सॉफ्टवेयर से लिंक करूँ, और इसको हम फाइनाइट एलिमेंट एनालिसिस एनसिस के साथ भी लिंकअप करें। तो अभी तो अगली मैं वीडियोज़ आपको दूंगा, तो उसमें हम इसको लिंकेज करेंगे। तो अभी इस वीडियो के बाद एक और वीडियो के लिए आपसे इजाज़त चाहते हैं। ज़िंदगी रही तो आपको कल तक इंशाल्लाह एक और वीडियो हम अपलोड करेंगे इसके ऊपर। बहुत थैंक यू।